Hello everyone. In this second video of Analytic Inverse Kinematics, we are going to work on first another example of analytic equations, and we are going to work on the 4 degree of freedom SCARA robot. And next we are going to talk about the important topic of kinematics decoupling. So let's get started. So here, let's say I have given you the end effector position given by xc, yc, and zc, and I also give you the rotation of the end effector with respect to the inertial frame, which is very similar to a rotation z matrix, but not perfectly. And the reason for it, if you remember from our previous videos, was the fact that when we did the DH convention, if you remember, the end effector frame that we had, it was like this. The z was down like that, and x was like this to the right, and y was like that. Okay, so this was x of the end effector, this was z of the end effector, this was y of the end effector. And the base frame, this one was x, this one, this direction was y. Now in this case it's different, okay? In this case it's a little bit different. You see here the direction of xc and yc is different, so I cannot go with that direction. In this case I have to go with this to match this coordinate that is shown in the picture. But it's not gonna make any difference to the direction of z of the base. So here this is xi, this is yi. And this is zi. So clearly, since z of the end effector and z of the I are in the basically opposite directions, that's why you get this -1. And also because the x and y, you see there are some twists as well. That's why this portion is not like a common z rotation matrix, because in a common z rotation matrix, this sign here up here is negative and that cosine is positive. So these changes are because of the twist in the axes and because of the direction of the z's that are opposite of each other. But in general, if you remember, the orientation of the end effector in general was given by angle θ1 plus θ2 minus θ4. And that's the same thing here. And the reason, if you remember again, for negative θ4 was this z, and the other two z's were opposite of each other. Okay, so don't be surprised if this does not look a perfect z rotation matrix. Okay, so now what I have here is the values of x, y, and z of the c point here, the end effector, are given, and also the rotation matrix is given like that, and we are going to find the 4 joint variables. θ1 and θ2, d3 and θ4. Well, since actually a SCARA is like a 2D planar arm, as you can see, plus an extension in the z direction with the d3 and then a spin angle θ4, so the equations, at least for θ1 and θ2 of the SCARA, could be very close or very similar to what we had for the 2 degree of freedom planar arm. Okay, so, and you can see that here. For example, if I ask you what is d3, well, if you look here, I have a constant d1, so in this case my first joint and second joint are not on the same plane. Okay, there is an elevation of d1 that you go up from the top of the first joint so that you get to the second joint, and that is what you see commonly in a SCARA. Okay, the first and the second rotation places, there is a difference in height between them. So this d1 parameter here is just a part of the geometry, as well as a1 and a2. Okay, these guys are fixed numbers, they are not to change. So if you see here, this point here is at D1, and if D3 is basically positive, if you remember the direction for the third axis about which the D3 was defined was also downward. If you go back and look at the previous video I made about the SCARA, you see that Z3 was also downward. So positive D means this guy goes down, okay? So clearly can say that Z of C is equal to what? D1 minus D3, right? Because when D3 gets bigger and bigger, your Z is going to go down and get closer and closer to the ground. So clearly from here you can find your D3, which is the unknown, the first unknown. It is going to be D1 minus ZC. D1 is a constant of the robot, ZC is given to me. There we go. So this is my prismatic displacement. D3 is D1 minus ZC. Not a big deal so far, very easy. What else? Okay, now if you look here at as I said, this portion of the robot, this is exactly like the 2DOF planar arm, right? A1, A2, theta 1, theta 2, it's perfectly the same thing. And this R is the square root of xc squared plus yc squared, so there is no difference here. Therefore, I can directly go and say theta 2 from those 2DOF planar arm, with the same technique that we used in the previous video, Analytical Inverse Kinematics Part 1. You see that we showed that theta 2 was arctangent 2 of plus minus 1 minus d squared and d, or plus minus a square root 1 minus d squared and d, where d was xe squared plus ye squared, and then minus a 1 squared minus a 2 squared divided by 2a1a 2, correct? It was a constant number, and using that I could determine theta 2 and also theta 1. If you remember, it was arctangent 2 of y of c and x of c minus arctangent 2 of, it was a2 sine of angle 2 and a1 plus a2 cosine of angle 2. Okay, so these were theta 2 and theta 1 from the last case, and the only remaining thing is theta 4 basically. And theta 4 here, as I said, theta 4 here, if you remember, I said this guy corresponds to, it's not perfectly like, but here this angle alpha, that is the orientation of the end effector's frame with respect to the original frame. This alpha, if you remember from our forward kinematics equations, this is theta 1 plus theta 2 minus theta 4. Okay, so if this R matrix that they gave me in general is something like what? R11, R12, R13, R21, R22, R23. And then let me move this out of the way. Also R31, R32, and R33, where clearly these are the 1, 3, 2, 3, 3, 1, 3, 2, they're all 0, and this guy is negative 1. So if you want, we can also write it this way. So in general, it is something like this. There are 4 numbers, 4 entries here at the location of the R's. Good. So now from here, how can I find alpha? Well, for alpha, I need what? Sine alpha and cosine alpha, which is R21 and R11. That's alpha. And guess what? I have calculated my theta 1 and 2. Once I know my alpha by an arctangent from this matrix, then I can find what? Theta 4. So from here, clearly, your theta 4, if you want to write it down, your theta number 4 is going to be theta number 1 plus theta number 2 minus angle alpha, where alpha is what? As I told you, it is arctangent 2 of R21 and R11. And there we go. You got all of your equations. This is all you need. If I give you the R matrix and XC, YC, ZC, and you know the dimensions A1, A2, and D1, from here you can get all of your 4 joint variables, and these are analytical functions. And again, clearly you see there are 2 solutions because of this plus and minus, elbow up and elbow down. For the Z direction, there is only 1 solution that comes in from here and here. Okay, of course, theta 4 can be 2 angles because there are 2 pairs of theta 1 and 2. But in general, there are 2 solutions for inverse kinematics of this. And again, if the point that we are asking is outside the workspace, you're not going to be able to touch it. Okay, so there is no solution. If it's on the boundary, you have 1 solution. If it's inside, you have what? You have 2 solutions. And here the workspace of this is similar to the 2DOF. So it is a disk like this, but it also has what? It also has a depth. So it is like this. It is a 3-dimensional version of the disk. Or actually it is an actual disk because any object in nature has 3 dimensions. Right? So it is something like that. Right? That's the workspace for this robot. Assuming that theta 1 can go full rotation, theta 2 can do full rotation, and let's say this is here as much as D3 can go up and down. Theta 4 is not going to affect anything here in this the size and dimension of the workspace. All it can do is whether your end effector is reaching the point like this, or for example like this, or like this, as long as these are all Z rotations. Okay, so it's not like exactly like that, so it's like this, or for example this or this. Oh. So this axis has to stay Z-axis, okay? It's not really a dexterous situation. It's not a dexterous robot. And one thing that it just came to my mind, I told you that if the point is outside the workspace, there is no solution, right? And I showed it to you that the radius of the big circle is A1 plus A2. The radius of the small circle is A1 minus A2, assuming that A1 is bigger than A2. Remember, I told you about that. Now, you can also show it here through this D. Well, you know, this D, if you remember, this D was cosine of theta 2. And you know, cosine of theta 2, cosine of any angle, is always between what? -1 and 1. So this D parameter here should be always between -1 and 1 if you want a solution for theta 2. And if you plug in here for D as whatever it is, which is this guy. Right? So if you do that, then you will get two things. One of them is that xe squared plus ye squared, or in this case c, right? We call it c, not e. So let's go with the same, let's stick to the same notation and not cause any confusion. Okay, we have to make sure that we stick to the same notation here, because we called everything C. In the previous lecture we called it E. It's not really anything major, it's just changing notation, but I always try in all my classes to stick as much possible as as much as possible to my constant notations I'm using and be consistent. So here, if I do this part side of it, this is what I will get. If I do the other part of it, I will get this one. Correct? So these are what I will get. And here, if I take my a1 squared and a2 squared to the other side, you will get that xc squared plus yc squared is less than or equal, and if you use the a1 plus a2, the whole thing squared, that is exactly going to be when you get these two terms to the other side. Correct? Because that's a1 squared plus a2 squared plus 2a1 a2. Right? And so from here, you see that your distance to the origin, the distance that you want from the end effector to the origin, has to be less than or equal what? a1 plus a2, the radius of the big circle. And if you do the bottom one here and take these to the other side again, you will get xc squared plus yc squared is bigger than or equal. This time this is a negative, so you will get a1 minus a2, the whole thing squared. And that means that the distance to the origin is bigger than a1 minus a2, the absolute value of it. And these are exactly the solutions that we specified for having a unique or two solutions. If there is no equality in any of these, there is what? In general, two solutions. If the equal parts are in, then either the top one or the bottom one, you are on the boundary, there is only one solution. If these guys are violated, then there is no solution. So these are the conditions for existence of solution for inverse kinematics for theta 2, right? And when you cannot find theta 2, of course you cannot find theta 1, because theta 1 depends on 2, and then you cannot also find theta 4, okay? So you cannot find any solution in general. Good, so hopefully it was clear. Now let's talk about the important topic called kinematics decoupling. So if you remember, I showed you in the very first slide that if I give you the general problem of inverse kinematics, you cannot necessarily solve it analytically. Why? Because you are solving several simultaneous nonlinear equations, and there is no general technique for solving these equations. Okay, there is nothing in math that is available for several of these. Now, in special cases, you can guarantee an analytic solution for the robots. What is that? So the robot has to have only 6 degrees of freedom. And it should have what? A spherical wrist. So if the robot has only 6 degrees of freedom and it has a spherical wrist, which we talked about it earlier, correct? A spherical wrist is basically a combination of 3 rotary joints that allow the end effector to take over any arbitrary orientation. The axis of actuation for all these 3 joints would intersect at a single point, correct, here, that we call this intersection point, we call it the wrist point here. Okay. If these 2 conditions are satisfied, then what you can do is, instead of, let's say here for this articulated robot, I have 6 degrees of freedom, all of them rotary, and I give you the orientation of the end effector with respect to the base. So I give you R of 6 with respect to 0. Also, I give you position of the end effector in base. I give you O of 6 in 0, correct? So I give you these. And then I ask you for what? I ask you for theta 1, theta 2, all the way to theta 6. And you know that here you have to solve what? 6 equations and 6 unknowns, and your equations are going to be highly nonlinear. Okay? Some of these parameters would affect, actually all of them in this case would affect the orientation. And I assume you can say that all of them would affect the position, but the matter of fact is that's not necessarily the case. The matter of fact is, if it's a spherical joint, really, it's only, for the case of this robot, it's only the first 3 joints that would affect the position of the end effector. Why? Because if I know the first 3 angles, which is the angle of this one, the angle of this one, and the angle of this one. If I know these angles, then I can determine, since from here to here this is a fixed length, okay, I can determine the location of this wrist point. And again, since from the wrist to the end effector is also a specific distance, also d6, so the location of the end effector could be determined once I know the angle of basically this rotation. So it's not like, for example, this theta 6 here, this guy is going to affect the position of the end effector, right? And theta 5 also is going to affect what? The position of the end effector, but not the position of the wrist point. Okay, so if I focus only on the wrist point, not on the end effector, then I can say the wrist point, the position of it, is only affected by what? By theta 1, 2, and 3. Even theta 4 is not going to affect it. It's just going to spin this axis. It's not going to affect the position of the wrist point. So while all of the angles except for theta 6 are going to affect the position of the end effector, only the first 3 are going to affect the location of the wrist point. So if instead of focusing on the position of the end effector, I focus on the position of the wrist, instead of 6 parameters involving in it, I'm going to deal with 3 parameters involving in it. And that problem, we call it inverse position problem. That can give me the first 3 angles. Once I know the first 3 angles, and I also know the rotation of 6 with respect to 3, I can find the rotation that the last 3 joints would give me. And so using that rotation matrix, I can find the last 3 joints. That problem we call inverse orientation problem that we discussed in some previous videos. So basically, if these two conditions, 6 DOF exactly and spherical wrist, are there, I will break my 6 equations and 6 unknowns. I will break my 6 equations and 6 unknowns, which is what I have over here. I break it into what? A 3 equation and 3 unknowns set or subset, and another 3 equations and 3 unknowns subset. So I break it into 2 subsets, where one of them is only dealing with finding the position of this wrist point based on the first 3 angles. The other one talks about finding the orientation that you want based on the last 3 angles and of course the first 3 angles. Okay, but you really will solve for 3 unknowns and 3 equations. I'll show you. So one of them is called inverse orientation problem. The other one is called what? Inverse position problem. So we can separate the position problem from orientation, and that is what we call kinematic decoupling. We decouple the orientation problem from the position problem, okay? Now, how do we do it? Let's focus here, and I'll show you with details exactly what is it that we need to do. Okay, so hopefully the idea of decoupling is clear, breaking down 6 equations, 6 unknowns into 2 sets of 3 and 3, where we can solve each one easily. And then that's just the idea of divide and conquer, right? So let's take a look here. First problem, what? Inverse position problem. So here, for the inverse position problem, if I know the position of the wrist, so these XC, YC, and ZC, these are the wrist coordinates. If I know the wrist coordinates, as I told you, it is only a function of the first 3 angles. And then I can find the first 3 angles. But the first question is, where do I get these wrist coordinates? So for that, I need to go back to this previous picture one more time. And I'll show you how you can find the wrist coordinates using the information given to me. Okay, so for that, I need to do a little bit of cleaning. It's just too messy in here. There we go. So, as I said, the end effector position and orientation are given to me, so I know this guy. D6 is just a fixed distance, and I also know what? R of 6 with respect to 0. This one is also given to me. Now, how do I get the location of the wrist, which is this vector here in green? How do I get this guy? If I know the ones in blue, how do I get this guy in green? Well, it's not a hard thing to say that if I know this direction, if I know the unit vector in this direction, whatever it is, all I need is to basically say that O of the wrist with respect to frame 0 is equal to O of the end effector with respect to 0, correct, this one, and then minus d6, which is the length of this vector, correct, times the unit vector here, which is shown in red, whatever that unit vector is. Now the question is, what is that unit vector? What is that unit vector? Well, if you look here, you clearly see that unit vector is what? Based on this figure, it is Z5, right? It is Z5. That's the direction of the 5th Z-axis. which comes from a spherical joint. Good. Spherical wrist, I'm sorry. So if you don't mind, I am going to write it like that. So if I knew what is Z5, if I could write this vector Z5 in which frame? In frame 0, if I could somehow get this basically in frame 0, that's it. Because this is a part of the geometry, this one is given to me, and this one, if I can somehow find, it's over. I can get the position of the wrist with respect to frame 0, and this guy I call what? X of C, Y of C, and Z of C that I need in that next picture here. So how do I get Z5? Well, Z5 and also Z6, all of these, they're all the same direction. If you use the approach that we did for the gripper and call this guy Z6, you see that Z5 and Z6 are in the same direction. So instead of Z5, I can also use Z6. But what is Z6? If you remember this rotation matrix of 6 with respect to 0, which is given to me, what's the definition of this? It is x6 projected along what? Projected along x0, y0, and z0, correct? That's the first column of this guy. Then I have y6 projected along x0, y0, and z0. Yes? And then the last column is z6 projected along x0, y6 the same z6 projected along y0, and the same z6 projected along z0. Right? That's the definition of this rotation matrix that is given to me. Now, what is this last column? If you look at this very last column, what is that? Isn't that the same as Z6 in frame 0? Of course it is. That's how you describe the vector Z6 in frame 0, so that's all I need. The last column of R, correct? The last column of this R matrix is all that I need. That's all that I need. That will be basically Z5 or Z6. Here, the Z6 and Z5, as I said, are the same thing. So here, instead of Z5, I can also use Z6, right? And what is that, as I said? It's the third column of the matrix R. And in general, I can show the numbers of that third column to be what? R1, 3, R2, 3, and R3, 3, right? When this R matrix is some general components like this. Clearly, you see, it is what? This last column, the numbers in this last column are that unit vector that I'm after. Correct? So that's all I need. This one is given. This is the last column of the R matrix, and I can also write it like this. I can say this is O of 6 in frame 0 minus D6, which is just a number. How do I get the last column of a matrix? All I need is to multiply that matrix by 0, 0, 1. When I multiply this matrix or any matrix by 0, 0, 1, the result of this is the last column. Correct? So that's all I need. There we go. All I need is to apply this formula here. And since everything in this formula is known, that is enough to give me the location of the wrist. Done. This is what I need. Okay, so let me highlight it for you here. This is how I get the location of the wrist. Good. So now go here. So now I know how to get the location of the wrist. Perfect. Now the location of the wrist, as we talked about, is purely a function of the first three angles. And if we go back here, you can easily see why. Correct? I told you. 1, 2, and 3, clearly when you rotate them, this point here, the location of it would change. But the last angle right before the wrist, which is theta 4, this guy is just a spin. It's not going to change the location of the wrist. So it is very clear to say only theta 1, 2, and 3 are going to affect the location of the wrist. So you see, this problem is now what I call inverse position problem. Because all I'm after is I'm given the position of a point, which is the wrist, and I need to find the three angles making that happen. So here is what we call the inverse position problem. How do I do it? Well, it depends on what kind of robot is the first three joints. In this case, it's just RRR. All of them are rotary. But even if the first three joints were not RRR, it was like RPP or PPP, or it was RRP, any of those formats, Cartesian, cylindrical, spherical, or articulated like this. There were four major versions, if you remember from the first lecture, which was a categorization of the robots based on the first three joints. There are four major forms. Here, this is kind of like the hardest one, all of them theta. When one or two of them are prismatic, it's so simple, the inverse position problem. So this is like the hardest one. And here we are going to focus on that, and I show you if I know the location of the wrist, how do I get the three angles, theta 1, 2, and 3? Well, all I need here to look at this guy in 3D and try to use some simple geometry to determine the angles. Well, if you look at theta 1, you see clearly theta 1 has XC and YC in a triangle, so it is very obvious from here that your theta 1 is what? R tangent 2 of Y of C and X of C. Done. Just as simple as that, I can get what? I can get my theta 1 just like that. Why? Because it is in this right triangle. Perfect. That's theta 1. Now what? Now let's focus on theta 2 and 3. Well, if you look at theta 2 and 3, they look like the planar arm. They are on this plane, on this rotated plane, 2 and 3. Where, again, if you look in this direction, you look at it from the side, you clearly see this picture. Let me give it some more, a larger angle. So you see this. Where this is the length of one of the members, correct? So here this D1 is just the length of this first member. It's just a constant number. And then you can call these guys whatever you want. You might just call them A2 and A3. It's just up to you. So let's call them A2 and A3. So this is A2, this is A3. This angle is theta 2. And this angle is theta 3. And what are the axes? The axes are not X and Y. One of them is the R axis, the other one is the S axis, where S here, this point is, if you look at it, it is z of c, this whole thing, minus what? d1. So this point here is z of c minus d1, and this point here is, as you can see, r, this hypotenuse, where r can clearly, that's the same as this r, can come from what? This is the square root of xc squared plus what? yc squared. So anyways, they are given numbers because xc, yc, zc, they are all given. d1 is just a part of geometry. That one is given. a2 and a3 are given. You need to find theta 2 and theta 3, and this is exactly similar to the 2D planar arm, right? So if you change some notation, it should not be hard to show that. In this case, let me bring them all in one place. So that was your theta 1. You can also show that your theta 3 is equal to arctangent 2 of plus minus 1 minus d squared under square root and d, where d was the horizontal component squared plus the vertical component squared. So this is going to be x of c squared plus y of c squared plus z of c minus d1 squared minus a2 squared minus a3 squared divided by 2a2 a3. Okay, if you get this one, that means you got your theta number 3. And then you can also find your theta number 2 the same way that you did theta number 1 for the planar arm. So here your theta 2 is going to be arctangent 2 of zc minus d1 and this square root minus arctangent 2 of a3 sine of theta 3 and a3 cosine of theta 3 plus a2. There we go. Okay, so here I can easily get what? All 3 angles calculated based on the location of the wrist, xc, yc, zc. If I have it, I can calculate all of the first 3 angles, and that is amazing because my inverse position problem is done. Now, before I jump into the next part, which is inverse orientation, here I need to talk about a couple of things here. One of that is the problem of singularity. Okay, so here, if you look at the first 3 joints, right, and point ZC, one problem that can arise is that this point ZC that is calculated, it falls onto the Z0 axis. So one case could be that this point ZC here falls on, so this is the wrist point C. Okay, so this is ZC now. If it falls onto the Z0 axis, we're going to have some problem. We are going to have some problem. Why? If you take a look here, What set of angles, theta 1, theta 2, theta 3, are going to give me that position? Well, the matter of fact is here, theta 1 is not going to be any important. All I need is angle theta 2 and angle theta 3. These guys are enough to give me what? That location. If that z is within the workspace and I can reach it, then all I need is theta 2 and theta 3 to make it happen. This theta 1 here is going to be irrelevant. Why? Because I don't care about how I reach there, at what orientation of theta 1. I can reach it like this, or I can reach it like what? Like this one. I can reach it like this. The very same thing, but then this guy comes here. And let me do a little better job. You see? And it can go all around, so theta 1 can take on any value you want, as long as your theta 2 stays basically at literally the same angle, and theta 3 stays at the same angle. As you can see, it doesn't matter what theta 1 is, you can go all around, and here this goes around the circle, and all of them will reach that point. So if this happens, means there are what? There are infinitely many solutions for theta 1. Means you cannot uniquely determine a solution, and that is, if you remember from the past, that is one specific definition that we use for singularity. Singularity means those positions and orientations that are given to me for n effector for which I cannot find a unique set of solutions, or at least several, a finite number of solutions, right? So if I find 2 or 3 or 5 solutions, that still is not a singularity. But when it's ambiguous, there is nothing to force theta 1 to take over any specific value or values, finite values, that means a singularity. Okay, so the inverse position problem here can have a singularity should the x of c and y of c are 0. So in this case, x of c is equal to y of c equal 0, but z of c is non-zero. And you clearly can see that if you look at the formula for theta 1, it is going to be arctangent of 0 and 0, really, which is ambiguous, right? Because there is no angle for which we have both sine and cosine to be 0. So this formula is not going to give you anything about theta 1. Now, one of the approaches to avoid singularity for this RRR robot, right, this articulated robot, is to what we call add a shoulder. So instead of your second joint to be right above the first joint, you give it some lateral offset here, and you call this distance here, basically, you call this a shoulder. When you do that, and when you look from the side, you will see something like this. This is your theta 1 that can rotate, But now your theta 2 and your theta 3, basically, whatever you do with theta 2 and 3, because of this shoulder D that you have, your rest point, or if you put an end effector there, cannot reach right above here, okay? Because these two are now on a plane which has offset about the plane that is passing through this Z0 axis. So this point will never reach somewhere there because it has always some offset from it. And this D, even a small bit of it, is enough to avoid your XC and YC become both 0 and your wrist goes right above the top of the first joint. So a small shoulder is enough to avoid singularity. Now you won't be able to reach exactly the points on the top of the end effector, the base. Not only that, also with the radius of D around that Z0 axis, you are not going to be able to access anything, but maybe that's not what you want, right? So here in this cylinder, that's the radius of which is D, you're not going to access any point over there, but if you don't care about it, that can avoid your singularity, okay? So that's one of the things that robotics engineers do. They try to design the robots so that they don't have singularity. One other thing we need to discuss are these 4 configurations here, that using which you can reach a specific rest point. So if I give you exact values of X, Y, and Z of C and say, hey, reach that, there are 4 different ways that you can do it. Okay, there are 4 ways that you should be able to do that. One is here, you reach it with this angle theta 1. Your links 2 and 3 are on the other side of the robot. If you look from the side and say, hey, this is like, if this is like a human and it has another set of arms here, correct? So if it has something like that, then you can say, hey, these 2 are the right hand of the robot, these 2 are what? The left hand of the robot. So this configuration that you have, you call it left. And if you look in this direction, the links 2 and 3 are in this configuration. And if you remember, when we had 2 degree of freedom planar arm, if you remember, we had these 2 different versions for reaching the same point. And this one, if you remember, we called it elbow down. And this configuration, we called it what? We called it elbow up. So this configuration where elbow is up and it is on the left side, we call it left and above. Okay, that's one way to reach the point, is using the configuration called left and above. Another way is the arm and the forearm comes to the right side of the shoulder, so we call it right. Still the elbow is up, so we call it right and above. Now pay attention that this theta 1, if this is theta 1 and this is also another theta 1, maybe this one you can call it theta 1 prime. Theta 1 prime and theta 1 are not basically the same thing, plus and minus 180. They are not. Because remember, you have a shoulder. So if you look from the top in here, and this is the base of the robot, and this is, let's say, a point here. I mean, if the point is exactly in front here, right, along the X of the base, then yes, because you have here some shoulder, correct? Right? This is one arm, this is the other arm. Of course you cannot reach it. So what you need is to rotate like this so that these 2 can reach it like that. And here in the opposite case, you have to go and reach it like this. So as you can see, the difference between these two angles, right, or the angle between them, is not 180. It's not like one of them is up like this, the other one is down like that. No, because of this offset, you cannot reach all of these points. So here, the difference between these two thetas is not 180, okay? Just keep that in mind because of the shoulder. So you clearly see I have right and above, left and above, and then I have left and below, and I have right and below. Okay, so there are 4 solutions here for the inverse position problem for the same values of xc, yc, and zc. Correct? So here you have the same theta 1 for these, and for these two you have the same theta 1, so you might call both of them theta 1 prime. And then theta 2 for these guys, which is up, if you remember, theta 3 actually in this case. Theta 3 for the up positions is negative, and for these down positions, theta 3 is positive. Okay, and you clearly know theta 3 has 2 solutions, right? Because of this positive and negative set. There are 2 solutions, and based on that 2 theta 3s, you have 2 theta 2s. Now the only thing is, why is it that you get 2 theta 1s out of this quadrant corrected xc and yc? Well, if you remember here, if you go back to one of these pictures that I made for you here, you can see why, right? So this is the base of the robot. The point I want to reach is here in the first quadrant. And as I told you, one way to access it is with something like this. The other way you can access it is with something like this. Okay, so there are 2 solutions for theta 1, there are 2 solutions for theta 3, and based on that too. So in general, just keep in mind that there are 4 solutions to the inverse position problem. Good. Now what about the inverse orientation problem? What do we do about that? Well, now that I got my first 3 angles, since I have the first 3 angles from these, I can find the rotation matrix of frame 3 with respect to frame 0, correct? Because you can write it as r of 1 with respect to 0, which is only a function of theta 1, times r of 2 with respect to 1, which is a function of theta 2, times r of 3 with respect to 2, which is a function of theta 3. When I know theta 1, 2, 3, and I know they are about what axis, I can easily get my what? Rotation matrix of frame 3 with respect to frame 0. Yes, good, I can have that. So now when I come to the orientation problem, I can calculate r of 6 with respect to 3, r of the end effector with respect to frame 3. How? Well, let's take a look. R of 6 with respect to 0, which is given to me, orientation of the end effector, this is given to me. It is equal to r of 3 with respect to 0 times r of 6 with respect to 3. This is given to me. This guy I just could calculate from the first 3 angles. So this one I also have. So clearly from here, what is r of 3 with respect to 6? You clearly see this is equal to what? right? Take the transpose of R of 0 with respect to 3, or which is the same as inverse of that, multiply from left side, and this is what you get. So from here, I can get this rotation matrix, 6 with respect to 3. And now, what's specific with 6 with respect to 3? If we go back to that spherical wrist here, right? If you look, 3 here is where? Let's look at Z3. Z3 is like that. So this is the same as this guy. So Z3 is this. This is Z3. Uh, 0, 1, 2, 3. And yes, that are the axes for joint forward, that's right. And then we also have X3 and Y3, but this is frame 3, correct? And if you look, frame 6, which is attached to the end effector in whatever direction that you describe, so a frame like this and some frame like that. Let me move it a little bit forward so we can see better. So this is frame 3. This guy here is frame 6. Do a little bit of cleanup here so that you guys can see a lot better. So that's frame 3. This is frame 6. The orientation of 6 with respect to 3 comes from what angles? Well, clearly it only comes from angle theta 4, angle theta 5, and angle theta 6, correct? Because it's 6 with respect to 3, not 6 with respect to 0. So that's just the angles of the end effector with respect to the first joint, basically, or the coordinate frame attached to the first joint. And that is clearly a function of theta 4, 5, and 6. Basically, it is this guy here that I can find now. This is equal to the rotation matrix of 4 with respect to 3 of theta 4 times rotation of 5 with respect to 4 of theta 5 times rotation of 6 with respect to 5 of theta 6. This is this guy. You clearly see it is only a function of these 3 angles. Good. So if I give you a rotation matrix and say, hey, I calculated this based on this formula, and it is some general rotation matrix like this with 9 entries, could you give me the 3 angles, 4, 5, and 6? And the answer is, of course I can. Here, all I need is to go from a rotation matrix to 3 angles. And one of the obvious solutions cases that you have, if you remember, was Euler angles. If you look at these 4, 5, and 6, they are actually just like Euler angles, right? Just let's go back and look at them. Just look. One is about this axis, the next one is about this one, and the next one is another spin. So the first one and the last one are like spins, that one is like a tilt. So clearly this is an Euler sequence that is what we call proper Euler sequence. the first axis and the last axis are the same type, right? So it's like something like zxz, zyz, xyx, right? yx, y, and so on. Now, which one? Here, I made this picture to kind of clarify it for you. So this is the spherical wrist, and these are the axes of frames 3, 4, 5, and 6 that we had in the forward kinematics using DH method. And as you can see, the first rotation is clearly about the z-axis, right? It's about z number 3, and the rotation angle is theta 4. So you go to the next configuration, and if you look, the axis of the second joint was really y3 axis, right? It was y3, which now, based on what we had in Euler angles, the z3 stays the same as z4, or z4 is the same as z3, but x3 and y3 are rotated into x4 and y4, and now that y3 now becomes y4, that's the axis of the second joint. So the second rotation is going to happen about the y-axis with angle theta 5. So the next rotation is rotation y and theta 5. And then the last joint, for which the axis was really z4, now z4 is turned into z5, and the last rotation is rotation of theta 6 about z5. So if you look at this sequence and comparison of this, clearly this is the ZYZ sequence. Okay, so the set of last three angles of the robot, or the spherical angles, they are exactly corresponding to Euler angle ZYZ sequence. So if we go and look here, go back, we have to say this is equivalent to the rotation matrix coming from the three Euler angles of the ZYZ sequence. And here I have it from one of my lectures. So this is the ZYZ sequence, and clearly you can now say your theta 4 is the same as the first Euler angle, which was psi, and psi clearly from here is arc tangent 2 of R32 and negative R31. Then your theta 5, which is the same as the middle Euler angle, or theta, it is equal to arc tangent 2 of, so if we square these two guys and take the square root plus and minus, so it is going to be R13 squared plus R23 squared. That will give you sine of theta, and then R33 is cosine theta. And finally, theta 6 here corresponds to the phi angle, which is arctangent 2 of clearly these guys, which is R23 and R13. Okay, so here you can find the last three angles, and your inverse kinematics problem is complete. We just broke it into two parts. The first three for position, the next three for orientation problems. Okay, the inverse orientation. And you can do this with any other robot, with the first three joints being different. So if the first three joints are not necessarily rotary joints, right? For example, like here, if I have this cylindrical robot with the spherical wrist, right? This is what we used for one of our previous lectures. Then what you have here is the equations for the last three joints are similar to what we did. It's just the first three joints, the inverse position problem, that the formulas for which is a little bit different. So here again, if you call this point the wrist point, and it has xc, yc, and zc, and if you call this physical distance L, now most of the time we neglect it in a spherical wrist, okay, and if you call this first distance between the first and second joint constant d, so d and r are part of geometry and they're given, And if XC, YC, ZC are given based on the method we talked about, well, let's see, where was it? It was, see if I can find it here. If we find XC, YC, ZC based on what we said here, so we have those and L and D, then clearly you see theta 1 here again is going to be arctangent to of YC and XC. D3 is clearly, if you add it to L, that is going to be equal to this rate, this hypotenuse, right? And hypotenuse was square root of x squared plus yc squared. So if you calculate that hypotenuse r and subtract L, constant L from it, that's your D3 prismatic variable, and then D2 clearly plus constant D is going to be ZC, so D2 is ZC minus D. So for all forms of R, which we just did, for this form, which is RPP, or it is RRP, or it is PPP. If you remember, these are the four major categorization of the robots based on the first three joints. It is very easy to solve the inverse position problem. I just did it for these two. For this one is extremely simple, and for this one you can also practice it on the Stanford robot. Okay, Stanford arm. So none of this is a hard thing. All of them have analytic solutions. And so for the last three joints, of course, we also have what? Our ZYZ sequence of the Euler angles. So you see, as long as you have what? You have a robot with 6 degrees of freedom and with the spherical joint wrist, you can always do kinematics decoupling, and there is a guarantee of analytic solution. Otherwise, there is no guarantee, okay? Especially when the robot is redundant, you have more variables. And solution analytically many times is impossible. So another important lesson is try not to make your robots redundant unless you have a good reason for it. Okay, because in general, any task you do for a redundant robot is way harder than a robot that has 6 degrees of freedom or less. Now, with less than 6 degrees of freedom, you cannot get much of dexterity, but maybe you don't need it. So you have to see what you really need, and based on that, try to solve the problem with minimal degrees of freedom. The more degree of freedom you add, the more link you add, the more joint you add. Any task we do, forward kinematics, inverse kinematics, later we calculate Jacobian, we calculate forces, torques, anything, control of it, anything you want to do is going to be significantly harder. Okay, and then the other problem is singularity. So if you can design your robot to avoid singularity, try to do so. If not, then you have to come up with a strategy to not be trapped in it. Okay, so there are too many details about the robots. Right now we are just looking at the basics, and hopefully as we move toward future lectures we discuss more and more here. So hopefully this was a useful video to you. Thank you, and I'll see you in the next lecture.